In this video, we're starting section 5.2 on a special type of exponential function, which is y equals e to the x power. Our goals for this section are first, we'll define what e is, and then sketching the graph of y equals e to the x and transformations of it, so when it gets shifted and when it gets reflected. All right, in this video, I want to focus on answering the question, well, what is e? Okay, so likely you would have seen this number before at some point in an algebra class, but let's introduce a scenario where this shows up. Okay, so suppose that we are investing $1,000 into a bank account. How much money would we have after 1 year if the account earns 4% interest per year, and that interest is compounded, part A says annually. Okay, so we're getting 4% interest and it's compounded annually. So, to figure that out, there's a couple ways I can do it. Like I know I have $1,000 initially, and if I'm getting 4% interest, if I convert that percentage to a decimal, as a decimal, that is 0.04. So if I multiply those, I get 40. So 40 is how much more money gets added to my account because of this interest I get. So in total, I would have 1,000 plus 40, which is 1,040. Okay, there's just a more succinct way that I could have gotten that answer. So let me talk about that. I'm actually going to erase this. So the more succinct way I could have arrived at that is to say, well, I could just take the 1,000 that I'm starting with, and I multiply it by 1 plus this interest rate converted to a decimal. So plus 0.04. So 1 plus 0.04, well, that becomes 1.04. And now if I multiply that by 1,000, that gives me 1,040. 1,000, and units are dollars. And that's how much I got the other way as well when I added the 40 to the 1,000. Okay. All right. Part B says, well, now what if we compound this interest monthly? So what does that mean? So instead of just getting interest once at the end of the year and having that just be 4%, now we are going to get interest every month. But because we're getting interest every month, we're going to cut this 4% into 12 chunks. So what that looks like is I will have 1,000, that's my starting value, times 1 plus, and then I divide this interest 0.04 by 12, because there are 12 months in a year. Okay, but I'm going to get this interest 12 times. So the way I indicate that is, well, I would have to multiply this by itself, 12 times. Okay, but I can express that more concisely as, well, just to the 12th power. Okay, and I can use a calculator to help me work out what this is, but this is approximately going to be equal to 1,040.7415 in dollars again. Okay, so it's a little bit more than what we got when we did it annually. Okay, part C, what about if I compound my interest daily? So daily, and let's assume it's 365 days in our year, so it's not a leap year. Well, it's going to be similar. I'll get 1,000, my starting amount, times 1 plus. This time I take my interest rate, that 0.04, and I divide it into 365 pieces. And my exponent's going to be 365, because I'm going to get the interest every single day, 365 times. Okay, so if I work that out, again with a calculator, it turns out that's about 1,040.8085. So a bit more. It's going up. Okay, so I might ask, is there a way to kind of get this interest continuously, like literally every instant? And what would that equal if I did that? Okay, so what I would do then is I would take the 1,000 that I started with, multiplied by 1 plus, and now I'm going to be taking that 0.04, and I want to divide it by infinity, because I want to be getting interest literally every instant, like infinitely often. So the mathematical symbol for infinity is we put like a figure eight type symbol, but it's rotated on its side. That's the symbol for infinity. Okay, and that also needs to be my exponent. My exponent needs to be infinity because I'm getting this interest literally every instant, infinitely often. So I have infinity as that denominator and my exponent. Okay, and it turns out if we work this out, and eventually in calculus you'll talk about some tools for how you can work this out, you get it's about 1040.81. So, even larger than what we had when we did a daily. Okay. And, in a sense, this is kind of like the best I can do. This is literally every instant. The interest is coming to me continuously. Okay. So it turns out that quantities that look like this, where I have a denominator and an exponent that are both getting really big like this, they show up quite often in math and applications. So what I'm going to do is let's investigate this expression. And I'm going to make one simplification. Let's say that this numerator, instead of being 0.04, let's make it a 1, just so it's a little bit simpler looking. And I want to investigate what happens as I make this denominator and this exponent get really, really big. So first, let's plug in 1 for that denominator and that exponent. So if I do that, it turns out that what it will equal is 2. If I plug in 1, right, it'll end up equaling 2 because I get 1 plus 1 over 1, and that whole thing to the 1 power. So this becomes 2 to the 1, which is 2. Okay. It turns out that if I plug in 10 for the n, well, now I'm going to need a calculator. And if I work it out, it's about 2.48832. That went to 5 decimal places. So it's larger. If I plug in 100 into both spots, it gets even larger. I'll get 2.70481. So bigger, but not that much bigger. If I go and plug in 1,000,000, I get 2.71828. Again, all of these values I'm rounding to 5 decimal places. There are actually more decimals though. So I noticed that at 1,000,000, it got a little bit bigger than it was when I plugged in 100, but not that much bigger. And it turns out that no matter how big of a number I plug in, it doesn't get very much bigger than this. Like the numbers, these outputs seem to be stagnating. They seem to be getting close to some value. Okay, and the value that they get close to has a special name, and I'm going to give a definition. So that number that these outputs seem to be getting really, really close to, like 2.7 something, 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 we call that number E. So the number E is defined as the value of this expression as n gets infinitely large. So as n gets infinitely large, this 2.7 thing, something, 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 we call that special number E. So E, it turns out, if I kept going like this and plugged in bigger and bigger numbers, it's about 2.71828. So that's correct to 5 decimal places. So actually, in fact, by the time I plugged in 1,000,000, I had those first 5 decimal places correct. It turns out later those decimal places aren't correct if I plug in 1,000,000. But if I kept plugging in infinitely bigger things, it turns out E ends up being approximately this. Okay, so a couple things about this. So E is an irrational number, meaning the decimals go on forever and they'll never repeat. So I mentioned that I made a simplification where I changed the 0.04 to a 1 in this table. So if I do have a 0.04 there, it turns out that the exact value of this, so not approximately, but the exact value is it will be 1,000 times e to the 0.04 power. That's the exact value. Okay, so this expressions of this form, and therefore e, show up a lot in applications. They show up in situations involving compound interest like this, as well as in exponential growth and decay problems. And these are things that show up quite often in calculus.